I am Jonathan Helmus. I work at Argonne National Lab, which is down in the southwest suburbs of Chicago. Today I'm going to be talking about speeding up Python data analysis using Cython. And because they gave me a long time period, I'm also going to tell some nice stories about weather radar to kind of give us an idea of what I'm using Cython for, instead of just jumping right into Cython. So a little about me. I started using Python in grad school when my advisor gave me a bunch of Fortran code, and I said there's got to be a better way. And I found the scientific Python ecosystem, and I started really loving it, and so I kind of just used it for everything. But I still kind of envy that speed that you can get in Fortran and C in compiled languages. And so when I discovered Cython, I kind of have the best of both worlds. So although I work at Argonne, the department that actually pays me is the Atmospheric Radiation Measurement Climate Research Facility, which we call ARM because that's way too much to say to anyone. So this is a United States Department of Energy program which collects data from in situ and remote sensing instruments, looks at the atmosphere, and it provides that information to scientists and researchers with a mission to improve the climate and Earth system models. So we have a bunch of different instruments at 3 different sites in the Southern Great Plains, in the North Slopes of Alaska, and we just opened a site in the Azores in the North Atlantic. We also can deploy instruments across the globe with some mobile facilities. And what's interesting to me is the program got a bunch of scanning cloud and precipitation radars with the American Recovery Act. We went from having about 3 radars to 30. And we're actually preparing some more radars for deployment later this year. Now, with all these new instruments, we said, okay, we need to make the data available to our users, and everyone said, well, we need software. We have no idea. We can't go buy that. So a colleague and I wrote the Python ARM Radar Toolkit, or PyArt, which is a Python module for reading, visualizing, correcting, and analyzing weather radar data. It uses packages from the scientific Python stack, so NumPy, SciPy. And development began to address the needs of the ARM program. So we wanted to eat our own dog food. We wanted to use this. But we have since expanded the project. It works with a variety of weather radars. For weather geeks, we can now read in and analyze NextRad, which is the network that's all over the United States. Probably if you see these big radar mosaics, and you see storms moving all over, that's probably a NextRad product. We also expanded our user base to include radar researchers, weather enthusiasts, and climate modelers. All the code is available on GitHub. It's open source under a BSD license. You can go check it out. You do have to compile this. If you don't like working with compilers and you happen to be using Anaconda or Conda, there are Conda packages available on Binstar. So how does a weather radar work? Well, we have a satellite or a dish, and we send out a microwave pulse. It propagates through the atmosphere until it hits something to scatter off, maybe precipitation, so rain, snow, hail. In some cases, you can also set it up so clouds. And some of the radiation returns back to the receiver. We look at multiple pulses, and we get a Doppler spectrum, which is just the power returned at different velocities. So how fast is that storm moving towards or away from the radar? That peak here we're interested in, we give some special names. So the height of it, or the intensity, is the reflectivity. That's what you see on the nightly news. Green means it's raining. Yellow and red, it's raining a lot. But we can also get the spectral width, which will tell us kind of how uniform the precipitation is. And the other interesting one is the location of that peak gives us the mean velocity, which tells us, is that storm moving towards or away from us, and how fast? And so a scan, we basically collect this whole spectra at every point along a long distance, so maybe every 100 meters, 500 meters, depending on the setup of your radar. Then you scan around in a circle, then you move up, and you do another scan. And so you can get an entire reflectivity. So this is from Hurricane, I believe, Irene in New York. You can also get spectral width, and you get velocity. And we'll come back to this velocity a little later in the talk. So it turns out there's lots of people that will make you a radar. And if you want to read that data, you have to go and ask them, well, how do I read your data? And they'll say, oh, use this. Then you ask the second vendor who made another radar, and they used a different format. So we have 3 different vendors in ARM. All 3 of them have different formats. And so you say, well, okay, we're going to have to write a lot of software to read this. Or you go and find that NASA, they were going to send up a satellite to look at precipitation, and they had the same problem. You know, we want to verify what we see with this satellite is true on the ground, and so we're going to use radars on the ground to validate that data. And so they wrote this was for the TRIM measurement. So they wrote the TRIM radar software library, or RSL as we like to call it. And this is a C library that's capable of reading a number of different radar formats. And it's really fast because it's written in C. And so we said, hey, we'd really like to be able to use that in Python, or I mean in PyArt, because then we don't have to worry about our I/O. We can just kind of rely on this nice fast library. And so we turned to Cython. So Cython, for those of you who've never heard of it, it's a Python to C translator. So it takes Python code and it generates C code. And then you can compile that C code to generate a Python extension module. The nice thing is it also adds some additions to the Python language that allows you to interact with C and C++ functions really easily. And a little later in the talk too, we'll see that you can also speed up pure Python code by adding some static type information. So the general workflow for using Cython is you take Cython files. These can just be Python files, but we give it a cool PYX, maybe it's extreme, I don't know. A different ending. We also have PXD. These are definition files. We'll talk about those a little bit. We run them through the Cython command line tool, and these will generate C files. You run those through your compiler. Maybe you link in some external libraries, and you get back a compiled Python module that you can import. So what do we do to be able to access these functionality of RSL in Python? So we have to create 2 files. The first is this PXD file, so this is a definition. For this, we just open up the RSL header file. So this tells us, what functions are being used in RSL, the various structures that it uses. And we just basically copy it and convert it into syntax that Python or Cython can understand. So it uses some structures. So this is just a way of storing data in a uniform manner. So we just convert these. And then we're also, for any functions that we want to use out of that library, we have to tell it, the compiler, what kind of types are going to get passed in, and what is that function going to return. Then the other thing is we actually have to make the interface. So we want to be able to call these C functions from inside Python. So we make an interface file. So this is going to look a lot like Python, but not completely. So for this, the first thing we want to do is cimport rsl.h. So we're using cimport because that way Cython's going to understand it. So this makes all these structures and functions that we've defined in this rsl_h file available in Python, or at least in Cython. In this case, we're going to define a class. This is a cdef class, so this is a little different. The difference here is that we can actually make some C-level attributes. So in this case, we're going to have pointers that can hold a radar. So this is an RSL structure, and a volume, another RSL structure. And we can define 2 special methods here. So there's a cinit. So this actually gets called before the Python init function. And this can do fun things can basically allocate memory if needed. And so in this case, we're going to give it the file name that we want to read, and we're going to pass that file name to this RSL any format to radar. So this is actually a C function in the RSL library that returns a radar structure. And we're going to store that because we've already made space in that class for the pointer to that structure. It can return null, so we have to do some null checking. We won't get nice error exceptions, and if we do. The other thing is, when that insubstantiated class, when that object falls out of scope, we want to free the memory that's associated with it. We actually have to keep track of that. It's not like Python where everything is nice. So we have to define a dunder deallocate method, and this is just going to call the RSL library and tell it, hey, we're not using that radar structure anymore. You can free the memory associated with it. And then beyond that, we can just define our normal Python functions, and we can make calls to these structures. So we can get a volume, and so that's just going to read the volume from the structure. We can also define properties and with the getters and setters. In this case, these are reading from the radar structure. It has a header that then contains a number of different parameters, but included in that are the month that the data was collected. So how do we actually build that? Well, the workflow is we're going to take those two files, that RSL interface and RSLH, run them through Cython, generate a .c file, compile those with GCC. During compile time, it's going to link with the RSL library that's hopefully been compiled beforehand, and then we're going to get an RSL interface file. That's top level. How do we do it in practice? Well, we put that all in our setup.py file. So this is using NumPy's distutils, which basically just lets you compile some things. They have a configuration object, and we're going to do we have to check to figure out where the actual path to RSL is. Some people put it in really strange places, so we need to be able to try and figure that out. But the meat and potatoes here is that we're going to call the add extension method off this config object. We give it a name of the extension module we're going to build, so RSL interface. The source code is this RSL interface.c file that was generated with Cython. And then we have to tell it, hey, when you build that, you're going to link in RSL. We have to give it a library directory and include paths. And RSL also has to be in the runtime, so it's going to link to the dynamic library. In this case, RSL isn't required for PyArt, so we also have some warnings that tell you, hey, you didn't build it with it, but you can continue on. So what does all this look like inside Python? So once you've built this, you can import the RSL interface module. This is just a Python module. You can run, dir on it, things like that. We can read in a file. So this is RSL interface, RSL file. So we've made a new class. We can look at that class. It doesn't have very good introspection, but we can then grab the month. We can set the month. And what this is actually doing is going into the C structure and setting parameters. And all this is really fast because it's all compiled C code. So let's return to radars for a minute. So we talked about how radars send out a microwave, and we get back a Doppler spectrum. The location of that peak is the velocity, which tells us is the storm coming towards us or away from us. And we can look at it. We can graph it. But if we look at this graph, you notice, so this scale's a little hard to read. This is 16 meters per second away from the radar, and this is 16 meters per second towards the radar. And you see there's gates that are right next to each other where the storm's coming towards us really, really fast, 16 meters per second, but then right next to it is going away from us. That can't be right, right? I mean, I don't usually see, clouds moving in opposite directions. So what's going on here? So it turns out if you have a velocity of your storm that's outside of the range that you measure, so in this case, this is the range we measure, and the actual velocity is way out here. So if you go to sampling theory, what happens is that peak gets folded into your actual sampled region. The amount that it's shifted is known as the Nyquist interval. So this is just basically this entire range. So these two limits are known as the Nyquist velocities. And so the velocity that we measure might differ from the actual velocity of the true atmosphere by this Nyquist interval. And in general, the true velocity of whatever the gate is equal to the velocity that we measure plus or minus some integer number of the Nyquist interval. And so a challenge for researchers is how do we derive these true velocities from the ones that we measure? And what that really comes down to is how do we figure out the number of Nyquist intervals to add to every gate in our volume? And so you can kind of start thinking about it, and you say, oh, we're going to develop some algorithms. And it turns out there's all kinds of algorithms out there that do this. One of our favorites is from the University of Washington. It's the real-time four-dimensional Dealiasing scheme. We call it 4DD. What this looks for is it looks in the three spatial dimensions, so up, down, left, right, top, bottom. And then it also looks in time. And it basically tries to minimize the gradient of the velocities in all those dimensions. What we like too is it's available in a source that we can include in PyArt. But if we take this velocity image, we see that there's lots of really stark contrast. There's dark greens again right next to reds. These are raw velocities from a C-band radar that ARM owns. We run it through the algorithm, and we get a much smoother result. We can see it kind of seems a little strange here, but this is actually a region that has a lot of noise, so we're not really too worried about that. So this also is a C library. And we have the source for it, but it's just C code. It's not actually a library. And so we want to use that too. And so we do a lot of the same thing as we did with RSL. We define a 4dd.h file. We grab the header information. We convert that into something that Cython understands. We also make an interface file where we're C importing this header again. And we're also importing the RSL volume. So this is actually from the RSL interface that we can import these classes. And so we're going to define a function that's actually going to do the Dealiasing. This is going to be available in Python. And what it's doing is it's calling this RSL interface, and it's copying the volume. And then it's calling 4dd and performing the actual Dealiasing. There's a bunch of parameters here, then we grab the data and return it. So building this module, it's very similar to building RSL. We take our files, we run them through Cython, and we're going to get this is actually should be 4dd interface. And our compiler, the difference here is we're going to also feed it the source files of 4dd. And it's also going to link against RSL because that's a dependency of 4dd. And we get compiled Python library. And just the setup of this, we have to include the sources. Again, we're adding this add extension. We give it the name of the extension, the sources, the library directories, much the same thing. So that works really well. It's fast because this is all C code. But every once in a while, we get something interesting. So this is a little toy problem that we had. This is some real data from one of our instruments, but it's heavily folded. We run this through 4dd, and we get really strange thing. This definitely doesn't look right. There's a big difference here, and that kind of looks weird. Well, if we calculate how many Nyquist intervals have been added to every gate in this, we can do that. The blue is 0, green is, I think, +1, and red is -1 here. And you can see, all right, we see where this error is coming from. We can kind of see that's probably wrong too. But what we see from this picture more importantly is you don't just flip a single gate. You don't add a Nyquist interval to one gate alone. You usually do it over an entire region of similar. So if we're going to add the Nyquist interval to one of these little red gates, we're going to do it to an entire region. So this gives us an idea for our own algorithm. So we're scientists, so we like to define algorithms. So we design our own. It's a two-step. The first thing is we say we're going to look for regions that have similar velocities. And we're going to segment our raw velocities into these regions. This is really fast. We use SciPy's ND image module. And you kind of can see the similarities. Then each of these segments we're going to say, should we flip one of them? And the way we do this is we model this as a graph. So each segment is a node, and then the number of gates that they share between them is just the number of edges. So in a really simple model, let's say we just had 3 segments. The number of shared gates is 6, 3, and 2 between this red, green, and blue. And what we do is we say, which one has the most connections? So it's the red and green one. We're going to unfold one against each other, one against the other by looking at all the velocities along that edge. And our algorithm just basically says whichever one's bigger, that one's probably correct, and we're going to flip the other one if needed. And so then we remove the one node from our network, and we have to recalculate the edges of any connected. And we continue on this until we have removed all the edges, and we're left with a single node. There's some other strange case. If you have 2 regions that are disconnected, then you have to deal with those. But so this ends up, if we go back to our toy problem, we run our algorithm on that, which I should say, we wrote all of this algorithm in Python. It's really nice. It lets you, prototype something really quick. We get a nice, smooth result. You can look at the number of Nyquist intervals. looks reasonable. And the only problem is this is really slow, at least slow for people who basically want to just do it now. So we profiled that code. So we're using Robert Kern's line profiler. This is available on SciPy. So we just add a profile decorator to our Dealiasing function. We have a little script that does it. And the results are that it's taken about 2.5 minutes to run over an entire volume, which isn't bad, but we can probably do better. And of that 153 seconds, 100 seconds is taken up in this single function that's this edge sum and count. And what this is doing is it's just looking at all the different segments and trying to find connections between them. I'm going to skip this slide, but so what we want to do is try and speed that up by adding some type information and converting that function into Cython. So I'm going to switch to a live demo. Hopefully this works. There we go. So let's rerun that profile. That's a little small. We'll see if we can't make that a little bigger. So let's actually, yeah, I didn't, let's kill that profile. So that's not actually going to work because first thing we have to do is actually, so we want to profile this DLS object, so we have to add a profile decorator. Yeah. Is it better if people in the back see, more or less? All right, so let's rerun that profile. While we're doing that, let's see what this function's actually doing. A really long doc string. So we're parsing some parameters. We can exclude some gates. What we're doing is we're looping over the sweeps, finding the Nyquist interval. This is actually performing. We're finding all those regions. And then this is the function that's probably taken a long time. We're finding the edge sums and counts. And so we moved that function into its own file. And we have this fast edge and finder. So let's see if that's done yet. So we're going to wait a second. So all this is just doing a line profile. I added this @ command because this prints out like an entire screen full of information. This is just pulling out the information on that function. If I had time, this takes about a minute, so there we go. It's just a little hard to read just because of the size. But so this is the edge sum and count function. And if you can count your numbers, so that's taking 47 seconds. So this is a little bit better than the slide that I showed before, but still 47 seconds, that's too long. And more importantly, that's taking 84% of the entire time of the dealiasing. And all this is doing is it's saying for every gate in the sweep, which is a 2-dimensional array, my 4 neighbors, are you in the same segment? If you are, I'm just going to continue on. If you're in a different segment, there's an edge. And then if if the gate next to it happens to be skipped, we can also exclude some. We're going to do, basically look around along that same dimension for a certain number of points. And all that is in this fast edge finding function. So let's add a little bit of information. So Cython can understand types. So what we love about Python is we don't have to worry about types, but that slows things down because it has to do type inference and things like that. So let's tell this Cython that this label array that or this label variable that we're passing in is a 2-dimensional array of integers. It is, so we don't have to worry about it. If it isn't, we will get a warning. But so we're going to remove that compiled library, the old one. We have to run Cython. This is going to generate the C code for that, and then we're going to recall our setup.py. So this is going to rebuild that that extension module. Then if we rerun our profile, so remember last time took about 49 seconds. We've added 10 characters to our source file maybe. We've told it that that label array is a two-dimensional array of integers. And if you count numbers carefully, we're now down to 4 seconds. So a tenfold increase by adding basically one line of code, and not even really a full line. But we can probably do better than that. So let's add some more information. So this is a two-dimensional array of floats. And these other parameters, these are just integers. They're basically flags. They're just Booleans. But the way we represent them are integers. Okay. So I have a little script that actually rebuilds that module. So we told Cython what all our inputs to that function are. We can rerun our profile. Last time it took about 4 seconds. It's the only part about demos. Sometimes you have things. All right. So now we're down to about 1.8 seconds, so another factor of 2 increase. But now you're kind of wondering, okay, we could probably continue this. We can add some more type information, but where should I add type information? What lines are actually taking a long time to run? So Cython has this nice little command, Cython-A. So this generates an annotated HTML file, which we will slip. Nope. Don't care about that. All right, that's a little, let's bump up the fonts here. Okay. So this is an annotated HTML file. So this is just our source code, but then it's got yellow highlighting. And what the yellow highlighting means is that if a line is highlighted, that means it's going to make calls to the Python C API. Those take a while. Those are computationally expensive. And so we want to try and remove that yellow. The other kind of fun thing is there's little plus marks here. So you can expand those and actually see the C source code that's being generated. Can be kind of helpful if you're trying to add some type information and don't know, why this particular thing is going off. So let's go back to our terminal. Let's add some more type information. So if you look at this, we're iterating over some indices. So these are just pulling values out of our two-dimensional arrays. So those are just integers. So we can let Cython know about those. So x index, y index. These right and bottom variables, these are just the size of that array. Those are integers also. So we can tell Cython about them. There's also some other variables. So this x check, this is just another variable that's kind of keeping track of if the neighbor happens to be ignored, it's going to keep track of another, basically, it's a big while loop. So those are also integers. So we added one more line. We told it about some more type information. If we remember last time, we were at about 1.8 seconds. Oops, I just built it twice. So if we rerun our profile, takes 5 seconds, I think. So we're now down to 800 milliseconds, so another factor of 2 about. So let's look at that annotated file and see what happened. So we regenerate it, hit refresh. So yellow's basically, we've removed a lot of yellow by defining these types. What's really interesting is these for loops are no longer yellow. So those aren't making calls to the Python C API. The nice thing is we're iterating over a range. It knows this is an integer. Cython is smart enough to basically translate that Python for loop into a pure C loop. And that really speeds things up. But we're still at like 800 milliseconds. Seems like we could probably do a little better. And we still have some yellow here. If we look at this, this is just grabbing a value from, we know that this labels array is, I think it's what? It's integers. This should be an integer also. So let's tell Cython about that. Let's say cdef int, so label is an integer. Also, neighbor is an integer. So that's just basically the segment number of the gate that we're looking at and its neighbor. So we can regenerate the annotated site or the annotated HTML file. We've seen these are getting a little less yellow, and we also have reduced these. So we can rebuild our extension module. And if we run the profile, we are at about 800 milliseconds on our last one. After adding this, we're now down to about 420. We can do one better, though. So we're also pulling values from this data array on this line. So those are going to be floats. Let's rebuild our annotated file. Look at that. So we've removed some a lot of yellow, but these things are still, why is just looking up a value in a two-dimensional array? Why does that have to make a call to the Python C API? Well, it turns out in Python you can do some really strange things when you're indexing. So you can use negative numbers. You can, if you say, oh, I want the 100th element of a length 10 list, it gives you an index error. In C, you just get, it would happily do it, and you'd get a segmentation fault. Well, it turns out we're not using any of that here. And so we can actually tell Cython, hey, you don't have to do those checks for the indexing. So let's do that. So the way we do that is we just use Cython bounds check equals false, and Cython wraparound false. So we can rebuild our function. I'll regenerate that HTML file. We'll start our profile, but if we update this, we now see we've completely removed the yellow from basically this entire nested for loop. So we should be getting some really good speeds. And if we look at this is now 195 milliseconds. So we started at 49 seconds. We've got it down to under 200 milliseconds. That's about a 250-fold increase. And just by adding about 5 lines to the script. So there's some other things in this file. It's in the PyArt source directory if you want to look at it. There's some fun things that we're doing with some classes. But let me go back to the slides real quick. Just one really cool one. So this is Hurricane Irene making landfall in New York. We can actually dealiase this. Nextrad's algorithm actually fails on this, so we were actually doing a little better. So just in conclusion, Cython is a Python to C translator. You can use it to wrap C and C+ libraries. You can also use it to incorporate C and C++ source code directly into your package. And you can also use it to speed up the execution time of Python code by adding static type information. With any remaining time, I'd be very happy to answer any questions that you might have. Yeah.
I saw that you were importing NumPy at the top. I know that's built with C2, but are you restricted to using specific Python modules to import it to your Python?
So Cython comes with bindings to a lot of the standard library and a lot of the C lib. It also has NumPy. I think it has some of the boost things. But you basically have to have those bindings. And Cython ships with some, but if you don't have those, then you have to go and find them. Yeah. So if you start to get to some, so it aims to work on any Python code. It won't necessarily give you a big speed up. Just compiling it down doesn't necessarily give a speed up. It's actually being able to add that type checking information. Currently, so Cython is still in version 0.20 or something, so it's still not fully. If you try and do like some yield from generators and a couple obscure things, it's going to fail. But most Python code, it will compile. Other questions? Yeah.
So it's a Python conference, so I might get in trouble asking this. But if C is faster, why not just do it in C?
So C is faster. Yeah, okay. So the question was, if C is faster, why not just write everything in C instead of using Python? C is faster in terms of computational time, but development time, which is usually the much more expansive part of development, C takes a long time. I mean, I actually like to use Fortran, but trying to work with strings and things in Fortran is a giant mess. And you can always build, you can go buy a 16-core machine for a couple $1,000s. How much salary of a developer will that buy you? Is the question I like to ask. Yeah.
So at what point do you go, all right, it's fast enough, and you go? I mean, it seems like you could just keep going on and adding more and more until it's essentially C. Is there a point where you start going, all right, it's fast enough?
So that really depends on the application. I mean, I like to kind of take it, if I know I'm going to use a function a lot. So this Dealiasing, we're going to run over terabytes of data. So I really spend a lot of time removing, basically generate a pure C function. But the syntax still is basically basically Python. It kind of depends on, once it's fast enough for you, that should be enough. The other thing is, if you've removed all those lines of yellow from your annotated file, you really can't do a whole lot better without then starting to look at algorithm improvement and things like that.
You actually wrote this thing just in C instead of bringing it to Cython because
So you do, there's some call overhead, so you'd reduce that. But there's some benchmarks on, I think, Cython's website that you can look at. Turns out, comparing to C, you can't do a whole lot better, but Fortran actually, the compilers are a little bit better, and you can actually sometimes get about a factor of 2 increase over even C. I think that's